afternoon, everyone. Thanks for having me here to talk to you about the development of an analog signal transmission in liquid argon for the DUNE experiment on behalf of the DUNE collaboration. So, I'm sorry, I just got an announcement of Zoom. So this is in the context of the DUNE experiment, which is a next generation long baseline neutrino experiment that you might have heard several talks already in this conference. In particular, this development concerns the far detector of DUNE that will be located at the Sanford Underground Research Facility. More in particular, the second module of the DUNE far detector, for which we are a new concept design is being proposed. This is the vertical drift liquid argon time projection chamber. This will be, just like the other modules, a 17 kiloton liquid argon time projection chamber. This concept was first introduced at the end of 2020, evolving from the experience that we've had with the operation of the protodunes at the CERN neutrino platform. And since then, a very intensive R&D campaign has taken place to demonstrate the feasibility of this type of detector. So just a brief overview of what a vertical drift detector would be like. As I said, it will be a liquid argon time projection chamber at the kiloton scale, and it will look like the drawing that you see here at the bottom. You would have the cathode suspended at mid-height horizontally and biased to minus 300 kilovolts. Surrounding the structure, there's the field cage. It's an independent structure that ensures the uniformity of the electric field at 500 volts per centimeters. And then the electrons would drift vertically towards the anodes located at the top and at the bottom of the detector, and which will be made of perforated printed circuit boards. This means that their fabrication is much simpler than the usual wire anodes and reduces the risk of having broken wires, but they have the peculiarity of being opaque. And the reason I bring this up is because I will talk to you about the photon detection system of this detector. The photons, you might know, are coming from liquid argon scintillators, and they're detected to provide the experiment with the trigger and the timestamp of the event. Because the photon detectors are usually placed in the anodes, and in this case the anodes are opaque, we need to find a different place to put them. This could be on the cryostat walls, like you can see here in the picture in the middle, behind the field cage structure. So this means we need to have a fairly transparent field cage, or alternatively, or complementarily, on the high voltage surfaces, just as the cathode, like you can see here on the pictures on both sides. If we put the sensors on the HV surfaces like the cathode, then we can achieve an extended coverage and therefore an enhanced performance of the photon detection system. However, this is conditional to us being able to supply power and to transmit the signal of the detectors using non-conducting materials. Just a bit of a comment on what detectors we plan to use. These are the X-Arapucas that you have actually might have heard. I saw some couple of talks and posters about these detectors. They are being developed for the first module of the DUNE far detector, and they're being modified mainly in shape for this second module. They would have a frame along which the CPAMs are placed surrounding the VUV light trap. And depending on whether they are mounted on the cryostat wall or on the cathode, they would be single or double-sided and have 80 or 160 CPAMs. In order to improve the light yield uniformity, we want to place them all over the cathode because it's the only structure available, and to add xenon doping to the liquid argon in order to increase the photon scattering length. So once these detectors are placed on the cathode, it would look like something like this. The signal would be taken to an electronics box, a smallest electronics box, that needs to be placed as close as possible to the detectors in order to avoid having long copper lines running across the cathode that will be made of a resistive material. So here in the bottom, you have a schematic of how this would be done. Here you have a schematic of the detector. The silicon PMs are connected together within the detector tile, and the signal is transmitted to an analog transmitter board that will amplify and transmit the signal to a fiber that will run to the outside of the cryostat towards a receiver that will convert the signal back to be digitized in warm. Just also a few words about how we plan to connect the CPAM, since this is a peculiar way. It's called a hybrid ganging circuit. You can see the schematic here on the top left. This is an example with just 20 CPAMs. This circuit provides an uniform bias for all the CPAMs connected to it and extracts the signal differentially in order to avoid having noise pickup between the detector and the transmitter. The CPAM ganging circuit is designed to avoid undershoot, signal distortion, and to provide a uniform recovery time. So what you can see here is a picture of a prototype of this board with the 20 CPAMs. It was tested and read out with a CPAM signal processor, that is a special equipment developed for the protodunes, achieving a signal-to-noise ratio of around 7, but it depends on the overvoltage of the CPAMs. Another particular feature is what was the measured single photoelectron signal between 50 and 100 microvolts with a 20 nanoseconds rise time and 150 nanoseconds fall time. So this is important to keep in mind since we're trying to transmit this single photoelectron signal using a cryogenic analog transmitter. There was no option commercially available. There are, of course, analog transmitters, even at a high bandwidth, but not that they would work right out of the box in a cryogenic temperature. But we had similar past and present experiences that indicated it's a feasible effort, particularly from the dark side collaboration. So we started the design based on the selection of specific discrete components. We need to keep in mind that the material that they're made of and the fabrication process should be such that it will behave well in cryogenic temperatures, that they have a large enough bandwidth. And I should mention that there's a fairly restricted number of such components available today in the market. We also had to design following some requirements, of course. First, that the power consumption would be small to comply with the power over fiber. This is the way we plan to power our devices over a fiber, and that they should transmit the signal in the dynamic range of the single photoelectron that I mentioned before, 2000 of photoelectrons. So this is a drawing that shows the basic idea of the transmitter. You have this differential signal arriving from the CPAM board that goes into a first and a second stage amplification, that together they are about 10 times amplification, but this can be adjusted depending on what the signal of the CPAM would look like. Then there's just a laser driver that transmits the signal and also sets a constant offset to ensure that the laser operates at its linear range. The power is supplied by a device that is power over fiber and goes through a voltage regulator to ensure a constant voltage. So this slide gives a bit more specifics of the design of this transmitter. I will not go too much into detail. You have the schematic here with the different aspects that I just mentioned. These are some of the components that after some trial and error, we selected that they work in cold. And these are two pictures of our two first prototypes. On the left, it's the first one, a single channel prototype. We connected to a laser that is pigtailed. And then the second prototype that we had has two channels and has lasers that have a connector, which is a bit nicer to test and to mount. Talking about the laser is quite an important choice in this scheme. We have chosen to use Fabry-Perot lasers at 1310 nanometer wavelengths. So we knew from the other experiences in this type of devices that the coupling of the fiber to the light source is a key aspect in cryogenic transmitters, but we have chosen lasers which are more efficient than LEDs. That is what usually is used. So a good coupling is less important. In addition, we knew from the literature that Fabry-Perot lasers have been shown to work well in cryogenic temperatures. So these are, on the left is one of the nice features. So what you see here is the laser output measured with our receiver as a function of the current in the laser. The red curve is in warm and the blue curve is when immersed in liquid nitrogen. So you see that the efficiency, the slope is the same, but the threshold current at which the laser starts to work is much lower. And this is interesting considering the power limitations. On the other hand, this is an example on the right of what why coupling could be an issue. You have, this is all done in warm. You have the laser with just the pigtail here in red. Then the second curve corresponds to the laser connected to one fiber, either 1 meter or 2 meters. There are two curves here. And the third one is when we connect one fiber after the other. So each time we reduce the output efficiency. Just a few words on the status of our R&D. We have the prototypes that I have shown you before, and they're capable of transmitting signals when they are in liquid nitrogen. So what you see here on the left are two examples of signals. The first one is very small signals coming from the silicon PMs with just picking up from light leaks in the dark box that we have. So this at this moment is about the smallest signals that we have managed to generate to transmit to the board, and it successfully transmits them. And this here on the bottom is when we pulse a LED to give light to the CPMs, and so this is a fairly large signal that is also transmitted. We are still doing performance studies also, for example, to prove that the system is linear through the entire range that we want. So here in the plot on the right, you have the output at the receiver that we're using as a function of the amplitude of an input signal. Here we're not using the CPMs, we're using a function generator to enter a small to big pulses, and the linearity is kept in this range.
2 minutes, Sabrina.
Yes. So we're still trying to understand what is the range in the transmission, so the studies are ongoing. And the latest achievement was to be able to test the full chain in cold, so the power over fiber, the CPMs, and the transmitter. And this is an example of the signal that was recorded. Just a few words on the receiver. It should just be an ultra-low noise transimpedance amplifier. We're testing in-house made or commercial options, but they have to have a large dynamic range. So this is what we need to take care of, but it doesn't seem to be a very hard task. And just to give a final comment on why we're doing this. So as I mentioned before, having this extended coverage will improve the performance on the photon detection system. There have been simulation studies that have shown this actual possible improvement. And I leave you here the link to Laura's talk that I think was the day before yesterday, and she described the simulation that they have been doing. In particular, for example, they would be able to improve the efficiency of the low energy trigger. I'm arriving to my conclusions. So having an enhanced photo detection system with an extended coverage is a very attractive option for the second Dune far detector module. The feasibility to do this, however, depends on two main things. Us being able to provide power over a fiber, which requires a very efficient photovoltaic converter that works in cold, and what I've just shown, which is the signal transmission over fiber, which is the analog option that I just showed you, or a digital option. We have an already working optical analog transmitter. It is under development, but it has been proved to work, and it will be tested as of very soon, as of next month, in a cold box test integrated to the other components of the proposed detector. I think that is all for me, so thank you very much.
That's really cool. Thanks a lot, Sabrina. Does anybody have any questions? We have just a minute for a question.
How much power?
Sorry, how much power we are consuming or we can consume?
You consume.
So the power consumption of this thing is super small. I think it's around, just let me do the math very quickly. It is taken, what did I see today? Sorry, it changes all the time. 40 milliwatts times. Less than 200 milliwatts, I think.
Cool. Well, thank you very much, Sabrina. Michael Febraro, you're up next. Sabrina, could you stop sharing? And there we go. Michael, you should be able to share yours.
All right. Hopefully my audio is clear.
Sounds good.
Okay. See this? All right. All right.
Yes,
So
you're
yeah,
good to go.
Okay, thank you. So yes, I'm Mike Probaro from Oak Ridge National Lab. So what I want to talk today about is a idea to use organic photosensors for detection of UV light. There we go. Okay. So the motivation here is basically that, as we think about, these next generation experiments, the size of these detectors keeps growing. And what it means is the aerial coverage needed for example, light collection is increasing. In the case of Dune, we're talking, each side is like, order 1,000 square meters, right? 60 by 15 or so. When we think about light readout, there's many ways to do this, but ideally, I think we'd like to have something that's directly VUV sensitive, so we don't have to deal with stability and such of wavelength shifters. If we're talking about pixelated readout systems, there's this idea that it'd be very useful to be simultaneous collection of light and charge. So in those applications, it would be nice to be able to do this with the same sensor. So what this really comes down to is we need large area, low cost VUV photosensors, low cost being the big point here. There's a lot of options people are looking at. There's the conventional PMTs with wavelength shifters, VUV sensitive SIPMs, light traps, of course, is being implemented. Gallium nitride is another material that's being looked at in of course of others. You heard earlier this week a talk from Jonathan Asadi on the use of amorphous selenium for this purpose. This talk is going to focus on a slightly different option, which is looking at organic semiconductors. So why organic semiconductors? Well, they have been exploding in the research and development of these devices. There's a lot of work looking into the use of them for solar energy, OLED displays, with cell phones and TVs, for example, monitors, displays, and as well as medical devices are really pushing this. They also extremely applicable for additive manufacturing techniques, such as roll-to-roll printing and other applications that can produce, 100-meter scale objects continuously. So there's a vast amount of knowledge and it's growing every day. And the question we've been asking is, can this be adapted for high energy physics experiments? Organic photo or semiconductors offer a lot of opportunities and not thought of in our conventional technologies. They're low cost, highly scalable. I mentioned roll-to-roll printing is already over 100-meter production rates. This is industry-driven technology, meaning it's going to get better every day, and there's a lot of active research in academic and industry, cell phones, displays, medical devices. They can be prepared on rigid and flexible surfaces. So for example, Samsung phone I show here is an example of that, a flexible semiconductor device. And one thing that I want to bring up is they can be prepared in stackable geometries. And this is kind of interesting because this allows for spectroscopic readout. What I mean by that is you can detect multiple colors. So I give an example here. If you think of an OLED, you can stack inorganic photoconductors or photosensors on top of each other, where the top layers are transparent to the wavelengths below. And this means that for the same surface area, you're able to transmit different colors. If we invert this geometry, or basically flip this device around, we can use this as a photosensor where we're able to pick up multiple colors to the same photo sensor area. So we're not losing photosensor coverage by having blue sensors and red sensors and filters and such. So this immediately brings ideas of maybe we can use this technology for, shrink off or scintillation separation as an example. Okay, so what is known about these devices so far? Well, as of last year, there's a paper in Science magazine that was published that reports the dark current rates and organic photodiodes have now reached, some of the best silicon technology. It's well below 0.1 picoamps in dark current rates. This paper actually reports 35 femtoamps. And there's ongoing research into exploring gain mechanisms in these devices. So external quantum efficiencies are well above 100% at this point. What I mean here is photons in, electrons out. But there are some big challenges with these technologies. They have typically slow response times. You don't think of organic molecules as very good conductors. Do they perform well in cryogenic conditions? What's their long-term stability? So these are things that we're going to have to address as we go on with this line of research. The way these devices actually work is kind of share some synergy with organic scintillators. So we have a conjugated system. In this case, we're actually increasing the conjugation to the point where you actually form quasi-continuous bands, right? So if we take a one-level system, we can keep splitting these up by adding more and more alternating double bonds to the point where you're actually forming something that looks like, is analogous to conduction and valence bands in a standard semiconductor. But remember, these are organic compounds. So the exciton diffusion length is very short in these devices. It's typically around 10 nanometers. So this limits the thickness of the devices you can produce if you were constructing them in a kind of typical planar geometry. Luckily, there is something called a bulk heterojunction geometry, where you literally combine P-type and N-type semiconductor materials together. In our lab, we just literally combine them in a beaker and then spin coat them on a material. And you're forming this heterojunction layer, which can be much thicker, which is needed to obtain good photoabsorption efficiency. This allows for thicker geometries. Okay. So the way we actually produce these devices in the lab is we first obtain, we need a transparent conductor. The one we typically use is ITO because it's widely available. So this is sputter coat onto a piece of glass, for example. Cleaning of the substrates are extremely important because all the layers of these devices are either spun coat or applied as a solution. So we need to obtain sufficient wettability if we're going to get good adhesion. We then apply the photoactive layer. Again, this is a liquid process. We use spin coating in our lab, but you can use slot die casting for roll-to-roll production. This is scalable to hundreds of meters. And then the electrodes are, the cathode is put on by thermal evaporation. So here's an example of an early device that we produced. Here's that device again, this time encapsulated. So the way this works is a photon comes in, we interact with the PN junction. In this case, it's P3HT and the molecule ICBA. This is a fullerene-based P-type material. We then separate the charge in that junction and collect it out in the readout. So this is an early device produced by our summer interns this year. And I show you a picture of what it looks like in a stacked geometry. So here's kind of the first data from those initial devices that we produced. Here's the IV curve showing an indeed diode-like response. Turn on voltage is around 0.4, 0.3 volts. And you can show sensitivity toward light, which is very good. We were looking at the timing response of this device by sending in a pulsed LED. You can see here the black line here is the actual LED pulse that we're sending it. And the blue line is the response of our photodiode. So you can see that there's clearly a fast and slow rise time. The rise time of the fast component is 425 nanoseconds, which is fast. It's on the fast end for these devices, but it's slow compared to what we typically think, SIPMs or PMTs. So one immediate thing that you can say from this is, if you're thinking about large area detectors, these might be a sensor that you could, for example, put in addition to PMT. So you do sparsely populated PMTs or SIPMs, but then the rest of this photo coverage area could be these type of organic semiconductors. All right. We also looked at the signal amplitude versus bias, shown here on the left. These devices can be run in either reverse bias mode or photoconductor mode, where we don't put a bias over them. And then on the right here is the spectral sensitivity of that device. So it's peaking at around 500 nanometers or so. But I want to point you to the low energy, high energy, low wavelength cutoff on this device. So what you're seeing there is this sharp decrease at about 350 nanometer. This is actually coming because of the optical transparency of ITO. So this is something that we quickly realized is going to be a challenge for this type of technology. But luckily, I was happy to see a paper just published put on the archive recently, which is kind of addressing this kind of issue. So the challenge for any kind of planar geometry photosensor is we need a transparent UV conductor. This is critical if we're going to make sensors sensitive to UV light. This recent paper on the archive suggests that P.PSS may function as a transparent conductor material. It's been measured now to have optical transparency of around 75% at 128 nanometer. So, you think of those early devices that we've been producing. If we flip the geometry of this, where we actually construct them kind of an inverted way, the top layer will actually be P.PSS. We've already confirmed that the PEIE is too thin to have any appreciable absorption. So then we should make it directly into the photoactive layer. So I think this is a path forward to dealing with the optical transparencies of the one conductor. Okay, so I hope I kind of thrown the idea out there that maybe we should be looking at organics photodiodes as a attractive solution for next generation experiments. There's a lot of information growing from academia and from industry on these devices. Their cost keeps going down as the industrial needs increase, so thus they are scalable. And I think what's particularly attractive is the ability to create stackable geometries, so producing spectroscopic photosensors that can distinguish color. Low temperature VUV wavelength is currently in progress. I show you here a setup that we produced at Oak Ridge. This is a VUV sensor platform where we've coupled a VUV monochromator to an optical cryostat. We have a windowless plasma light source that can go from 58 nanometer to 3200 nanometer, and we can probe temperature ranges from 5 to 500 degrees or 500 K. In addition, we've also, in collaboration with the University of Texas in Arlington, constructed a VUV pulse light source that can provide pulses, variable intensity from kind of the tens of thousand photons or 10,000 photons, single photon level. And I strongly encourage you to attend the talk tomorrow by Austin McDonald explaining the performance of this device. So measurements are in progress, and I think this technology is worth pursuing. I take any questions. Thank you.
Awesome. Thanks a lot, Michael. We've got several questions popping up. So it looks like first question from Carlos.
Well, very nice talk. Thank you for the talk. Brian, I have a question on your slide 6. You showed on the bottom of the plot, right side of the plot, a floor at 1.5 electron volts. Can you go lower than that?
The floor at 1.
A longer wavelength.
Oh, the 185?
Yeah.
No, so that's ethylene. So that's already a gas. So it would be very difficult to push much lower than that for the band gap. Yeah. So realistically, we need to have a length, in the visible to have enough. We need enough conjugation for a practical device that the device is going to be in visible wavelength for the band gap.
Okay, yeah. Thank you.
But the sensitivity will push down, of course.
Right.
Yep.
Brian, you had a question?
Yeah, thanks. So this is really cool. Can you talk a little bit about the timing resolution? What, physically, what drives that, and how one might make it faster if possible?
Yeah, so this is the big thing. If you look at a lot of the papers on organic semiconductors, they like to kind of use analogies similar to conventional semiconductors, but there's big differences. The charge transport mechanism here is almost like, I'm a scintillator guy. It's almost like scintillators. You're basically, energy is transferring via a hopping mechanism through fret. So that's what's limiting the timescales of these interactions. And it's hard to imagine getting around that. So that's really what's limiting these devices. I don't know if it's possible to make a device which would be faster than, for example, 100 nanoseconds. But I think, these can be in combination with other sensors because they're so cheap.
Yeah, I think that's very clear. Thank you.
Awesome. Unfortunately, we need to move to the next talk, so perhaps the remaining questions can go into the chat. Valerio, you're up next.
Yes, can you hear me?
I hear you, and you should be able to share your slides.
Okay, can you see the slides?
We've got it. I'll give you a 2-minute warning when that time comes.
Okay, thank you. So I'm going to talk about a new track imaging system we are currently studying to be used mostly for neutrino oscillation experiments. Now, we know that the probably most common technique currently used is the time projection chamber based on liquid argon. Due to the large large target mass, low energy threshold, and so on. This technique, however, needs some time to drift particles. Now, this most of the time is not a problem. We have a really low interaction rate when using neutrinos. But for a near detector of future experiment such as DUNE, this time could be a problem. So we are trying to study a way faster technique to overcome this limitation. The idea here is to basically take pictures of the charge tracks produced in the neutrino interaction. This is a sketch of what we would like to do. Basically, in the sand detector of the near complex of DUNE, we would like to put a volume of liquid argon, mostly to measure the neutrino argon cross section and study the Now, to take pictures of charge tracks, we need to be able to collect the light emitted by the argon and use that pictures to perform a 3D reconstruction. Now, this is challenging. You can see here the most crucial points of this technique. The main problem here is the wavelength of the light emitted by the argon. There is a peak at 128 millimeters. It implies a really low quantum efficiency of the sensors. We are talking about 10–15% of quantum efficiency. At the same time, we have really low transparency by the most common optical materials. At the same time, we need to preserve the direction of the photons, otherwise we can't make a photon. We also need to work at the cryogenic temperature, and we need a deep and wide field of view to be able to collect and see most of the light emitted in the volume. So it's quite challenging, but all of these will provide a much higher rate capability, because we are basically limited just by the electronics time and the time of the scintillation of the argon, which is much faster than the drift time of the SPC. We can also work in a magnetic field, and the cryogenic temperature help us with the noise of the sensors. Now, we studied different optical system used in this detector. We started with the lenses, twin lenses, Fresnel lenses, and metallic mirrors. But for different reasons, none of these was good enough. Sometimes due to the low transmittance of the lenses, or simply because the construction was very difficult or expensive. So we focused our attention on the coded aperture technique. This is a technique mostly used in the X and gamma ray astronomy. Is way less common in the particle physics scenario. But this offers some advantages compared to the other systems. It's really simple to make. We'll see in the next slides why. It offers a really good field of view and depth of field, and is not worse than the other materials when talking about the light can go through the optical system. So we are currently studying this. Now, to be a little bit more specific, this technique is basically an improved version of the pinhole camera. But instead of a single hole, we are using a lot of them. These holes, all these holes are commonly called a mask, and are arranged in a specific pattern. Now, the idea is that for each hole, a source light will project a copy of itself on the sensor, on a sensor behind the mask. Now, this recorded picture is, of course, not what we want. Is really a mess. Is a superposition of all the projected images from each single hole. But if the mask follows specific pattern, as I said, it is possible to decode the recorded picture and obtain again the reconstructed image, the original light source. So here is the really simple scheme, and here is a simulated basic example. Here we have a simulated source in the center of the volume. This is what a mask look like in reality. Here the white region are the duals, while the black one are the filled region. And here you can see the recorded picture. Now you can see these two are quite similar. This is because with a single light in the middle of the scene, what you get is just basically a zoomed in shadow of the mask. This is not the case for more complex sources, just because this is really simple. But from this, you can see that it is possible to obtain an image similar to the original one by the convolution of the recorded image. Now, to test this technique, we built a simple prototype. You can see here on the bottom right, the mask itself, as you can see, is basically a foil of metal with some holes in it. So it's really cheap and easy to make compared to lenses and mirrors. You can see here mounted on the support. We coupled it with a 8x8 SIPM matrix. Each SIPM is a 1x1 millimeter square area. And we used a LED coupled with an optical fiber to generate the two light above the system, the camera. You can see that it is both of them, one above the other here. Here, the results obtained from that prototype. In the top row, you can see what the results from a really simple simulation. Here we did not include anything related, so there is no crosstalk or after pulses or whatever. So this is really one of the best results we could get. And below, in the bottom row, you see the results obtained from the prototype. You can see that for the cases with only one light turned on, the results are quite similar, and you can easily see the single point. It's very a bit more difficult for the case of two light at the same time. You can still see the lights, but there is more noise, background noise. Now we are still studying this background. Most likely is caused by the alignment of the mask with the sensor. That must be really, really precise to avoid the degradation of the construction. And of course, also the associated noises after and cross that were not included in the simulation. Here you can see an example of what the sensor sees before the convolution. So it is basically not usable at all. The point here is that both the light points are still visible. So we are now trying to study this technique a little bit more, let's say, better. Let's say better. So we are now studying simulating in a more complete environment. We are using the Genie event generator as well as the Gen4 software. We have included all the important aspects of the physics and the geometry for this technique. So the scintillation of the argon, propagation, attenuation, scattering of the photons, and so on, as well as the exact geometry of the mask. You can see a detail here with all the holes, the sensor, and coupled in what we call a camera. Here is a detail of the geometry we are currently studying. So basically a cube with 6 cameras on one for phase, and some of the photon emitted by a muon crossing the volume from one angle. We also developed a custom code to include this time all the details of the electronics and the signal. So all the possible sources of noise, quantum efficiency, and so on are included. We have an article on arXiv with some more details on the coding process and what we want to do after we get 6 images to obtain the reconstructed 3D images. So you can find some information here. What we are doing now is, this is just an example of one image of the article. You can see here a simulated track as seen from 2 different planes, and the reconstruction of using this technique and in the geometry of the slab. So this is the prototype. These are the specifications we would like to use for a prototype.
2 minutes, Valerio.
Okay, thank you. That we want to build by the end of this year. We would like to use 6 cameras, as I said before, using 16 by 16 silicon photon multiplier matrix. And that's it. Basically, we would like to use this prototype to test it with the cosmic rays, or maybe on a beam. We will see. We started some tests on the hardware. We are now testing the cryogenic ASIC. We are waiting for the CPM matrix. Here is a 4x4, but in reality, we are waiting for different 8x8 matrix that will be arranged in a 2x2 pattern. You can see here the scheme of the channels to extract the signals, and the first test on at the cryogenic temperature probe at and this is the status. I leave just the conclusion here. That's it.
Oh, that's really clever. Thanks a lot, Valerio. Any questions? I see one question by Bolotnik.
Yes. Usually, code Aperture give you just direction to the source. How you can identify the location of your source, position of the source?
How can we identify the position of the source?
Yeah, how you locate the source or the source of the light? Because code Aperture give you only direction.
We know the field of view of this camera, so we can, knowing the number of pixels of the sensor and the reconstructed position of the image, you can obtain the position in the real space.
But this position of the image, it is not a geometrical coordinates, it's just an angle coordinate. Am I right, or I'm mistaken?
No, this is already a picture of the source, like a common camera, basically. But instead of a lens, we are using the mask. But this is exactly the position of the sources as seen by the camera.
Okay.
So yeah, the idea is to really reconstruct the image as a normal picture. It's just the optical system that is different.
Okay.
I think this needs to be used with like 2 or more cameras at different angles to get a
Yes,
3D
yes,
showing
yes.
construction. Yeah.
Okay,
Yes.
okay. Now I understand. So now it is different. Yeah. Okay.
Yes.
And also you have to somehow to compensate 50% efficiency loss of your system.
I'm sorry, I did not understand.
Because when you're using a mask, you lose 50% of the.
Yes, yes, yes. But as for now, there aren't the lenses or the mirror lost almost the same. So basically, it's not worth. We would like to find a system better than this, but for now, this seems to be the better. The light, the quantity of the light is a problem. 50% loss is really a lot, but we are not finding anything better for now.
Okay.
Yeah. Okay. Thank you very much. Okay.
Yeah. Thanks a lot, Valerio. And next up, we have Chris Stanford. Valerio, are you able to stop sharing?
Yes.
There we go. All right, Chris, we can hear you and we can see your slides.
Great, thank you. So I'm talking today about increasing photodetector light collection with meta lenses, and I'm talking on behalf of a group of us at Harvard, Fermilab, and IFIC. So what are meta lenses? And I'll start there. They are a type of metasurface. So a metasurface is a flat material with small sub-wavelength structures that are created on its surface through nanolithography techniques. And they essentially impart tunable phase delay on the light that's passing through it. And you can, based on the pattern you make on the surface, produce an arbitrary, far field pattern of light going through here. And there's a certain subcategory of metasurfaces called meta lenses, which use a certain kind of pattern to focus the light onto a point. And they've had some big developments in the last few years, particularly with the capacitor group at Harvard, which we're working very closely with. So in 2016, they demonstrated meta lenses for the visible wavelengths that achieve diffraction limited focusing. In 2018, they demonstrated achromatic meta lenses. So with the single meta lens, they were able to focus multiple wavelengths to the same point. And they've recently had some funding from industry to continue developing the technology. So it's a very new and exciting area of research. What we want to do is see how it could potentially be used in a particle physics detector. So our concept is to place these meta lenses in front of silicon photomultipliers. So with more modern detectors getting larger and larger, some coverage, like for example, the Dune detectors are looking at a SIPM coverage of on the order of 1% of the surface. So this concept, we would introduce a plane of meta lenses in front of the SIPM plane that would gather light that would have missed the SIPM and deflect it onto the photosensitive surface to increase the light collection. So you might wonder why we haven't been doing this with traditional lenses all this time. Well, traditional lenses are very expensive. They're bulky. They take up a lot of space in the detector, and they've got some optical limitations. Like for example, they can't pack very well. With meta lenses, they're thin, they're lightweight, they're very cheap and easy to mass produce. They use the same kind of lithography techniques, in fact, a very basic form that is used in a lot of like microchip foundries, for example. So they can be, you can make hundreds of thousands or millions of these very cheaply, and you can make them square shaped if you want. It's totally arbitrary what you want to do with these things. So we have some past work on that what we have published on this technology, which has just demonstrated that for light that is normally incident on a metal lens, you can increase the light collected, for example, on a 1.3 square millimeter SIPM by a factor of 6 or 7 by introducing like a 1 centimeter scale metal lens in front of it. Our current work is continuing to explore the use case of metal lenses in noble element detectors, which add some difficulties to what use has been studied so far. So in a detector, we don't have nice plane waves impacting the metasurface or the SIPM. We have photons coming from all sorts of different angles. And so that's one thing that we need to study. We need to study how effective the metasurface is in the non-ideal case. We also need to study how well it performs when submerged, because we expect the efficiency of a metasurface to be dependent on the difference of the index of refraction between the medium it's in and the material it's made of. So once you introduce a liquid, you expect the efficiency to drop. We also want to look at its cryogenic stability, whether or not these nanoscale structures can stand up to the temperatures that we want them to. And we were also wanting to explore the UV metal lenses so that we could potentially get around the need for a wavelength shifter in a noble element environment. So some of this we've already seen a lot of progress with. For example, the angular efficiency studies. We have a student, Ben, who's been building out Monte Carlo, in which he builds a detector volume and places a metal lens array on one side and determines what exactly we expect in terms of the incident angles from photons onto the metasurface. This is one of the key parameters in studying how effective they'll be. And it's very dependent on what the exact geometry of your detector is. So, if you have a reflector around the balls of your detector, then it changes what angles you expect. So we're looking at all sorts of detector designs and not really with any one particular design in mind. Something else regarding the angular efficiency is that we don't have a clear picture of what angle. This might sound crazy, but once a photon hits a metasurface, precisely what angle does it leave? The reason for this is that the current methods to simulating a metasurface are quite involved and take a lot of computation time, hours or days to compute the far field pattern rigorously. And if you want to do that, you have to pick an angle to do it at, and then run the simulation, and then just to figure out what it is with a 1 degree difference, you need to run that all over again. So exactly what happens at arbitrary impact angles is not something that's well understood in the, or at least not easy to simulate in the metal lens field. But one of our postdocs, Augusto, has developed a method in which he gets a very good approximation by dividing the metasurface up into regions, which are then approximated by just simple diffraction gratings. And he's able to achieve a very, so he builds basically a library of the particular metal lens, and then once that's built, which takes a while, but after that's built, computing what happens at different angles is relatively fast. So with this, you can get a very good approximation to the rigorous method, and it only takes about 2 minutes per different impact angle. We've also studied what happens when these nanostructures go under submersion in liquid nitrogen. So we were quite rough with these. We basically took a bare substrate with these nanopillars on it and dunked it into liquid nitrogen and held it there for a minute and just pulled it out and repeated the process multiple times, and then looked at the structures under an SEM, and we could not find any damage done to any of the pillars. So that was a good time. We also have done some submersion studies to determine how effective they would be in a noble liquid environment. And so so the main result was that we took, instead of a metal lens, we just took a diffraction grating, and we determined what fraction of light would pass through normally on an equal 0 mode, and then how much would get deflected towards the n equals 1 mode, which is the main measure of the efficiency of the grating, and ultimately a metal lens that you might make out of these metasurfaces. Once that was submerged in water, the efficiency went way down. We expected that, but maybe not quite that level. However, we introduced an air gap behind the posts and sealed that off from the surrounding liquid, and we were able to recover the efficiency. So there is some potential still to use this in a noble liquid environment. You just have to either surround, you basically have to create a vacuum pocket around the nanostructures. Finally, the next steps that we plan for our research, we would still like to develop metal lenses specifically for sub 200 nanometer wavelengths. We would like to confirm the simulations that Ben and Gusto have done with the angular incidence with a dedicated experiment. And then ultimately, we'd like to build a metal lens and a SIPM array and measure the increase in the efficiency in a noble element test stand. And that's it. Any questions?
That's really neat, Chris. Thanks a lot for sharing. We have just a moment for one quick question. What's necessary to reach sub 200 nanometer transmission through one of these metal lenses? Is it a different material for the posts?
That's a good question.
Okay.
It's a similar material. We plan to use UV transmissive fused silica.
Okay.
However, the difficulty and the reason this has not been done before is because the current leading edge in nanofabrication techniques can only produce structures with feature sizes that on the order of 100 nanometers, and we would like the power of the metal lens is really based on how small of a feature size you can get relative to the wavelength. You want them to be several times smaller. Yeah. And so for like 178 nanometer light, you want very on the scale of maybe 20 or 30 nanometers. The technology is just not there yet. However, in the fabrication industry, there have been new advances, and it is now actually possible to do that. The institutions that have that technology available are more rare, but they do exist now, and that's sort of what we're going to be pursuing.
Cool. All right, well, thanks a lot. If you can stop sharing, Evan Angelico is up next. And you should be able to share and speak. You can see your presentation.
Hi, everybody.
I see your slides. There we go.
Yeah. So my name is Evan Angelico. I'm a postdoc working with Giorgio Gross at Stanford, and I've been. I'm going to tell you about the Nexo charge readout modules, and in particular, integrating a cryogenic ASIC readout directly on the charge collection modules for this detector. All these people here have really been instrumental in this work, people from Stanford and from SLAC. This is a picture of the international distribution of the Nexo collaboration. We have a new collaborator from Munster, and a lot of other people also have contributed to this work, so I'd like to thank them. Nexo is a single phase liquid xenon TPC you may have heard about in previous talks. There's also another talk on Friday I'm going to point out on the top left. I'm not going to talk a lot about the detector sensitivity and specs and such. You may see some more in those other talks, but it's a discovery experiment for neutrino-less double beta decay, and it builds upon a previous experiment, XO200, which was largely successful. So a lot of things are similar, just scaled up for the Nexo detector. And the main observables for discovering neutrino-less double beta decay hinge on these following properties of events. And readout electronics, both in the light channel and the charge collection channel, are intimately tied to these parameters. So if you change some geometrical aspect of the charge readout, for example, it will affect one's sensitivity to all of these discriminants. XO200 used a wire grid style charge readout. This is one place in which Nexo is a little bit different. So Nexo is moving towards a deposited electrode pattern on a radio pure quartz substrate. So these are modules made out of quartz with evaporated gold conductor. And contrary to what you may see in the right as being an array of pads, the charge readout geometry is not an array of pads, because at the corners of each of these pads, they are connected. And that's a zoom in picture of a corner on the left, where there's a bridge of conductor at the corners so that you can gang these pads together in X and Y directions, and isolating them as an evaporated layer of silicon dioxide. So an event shown in blue would appear as two strips in X and Y lighting up, and you can do the position localization that way. So those are strips, and we'll call these tiles. This is a link to the pre-CDR, and it's showing an SEM picture of this sort of strip crossing being demonstrated. It looks pretty good. So these tiles, prototype tiles, have been made. In fact, here is one on the left at one of our test setups at Stanford. At Stanford, we have 30-kilogram liquid xenon TPC test facilities specifically for testing the prototype detector submodules for Nexo. And this one on the left is a quartz tile. The signals were not from the strips, are not wrapped around to the back of this tile. So instead, some wire bonds are made at the edges to connect the 32 strips to some wires that then go outside of the liquid xenon space through the feed-throughs in this conflat flange. Outside there are some charge preamplifiers that then send analog signals over 2 meters of cable to digitizers outside of the cryosat. And that works. It's not really ideal. This is a picture of an event showing that it demonstrating charge collection in these 2 strips, where there's a long time constant to that amplifier. And so the peak of the plateau here reads off the charge collected. As I was saying, it's not ideal to have all those analog signals traveling over such large distances, and detectors these days really need to implement amplification and digitization inside the liquid xenon right on the subdetector modules. So we're developing a readout that is attached to these charge modules, and it significantly improves hardware complexity at the system level. If you have many of these modules, having the electronics right on them simplifies it. It improves analog signal fidelity. Random noise is reduced because the random noise is largely dictated by input capacitances, which has to do with the geometry and how long conductors are. And external noise susceptibility is reduced when you have in xenon detector electronics. So this work is moving from the picture on the left to the right, where on the right you can see an ASIC and a board that attaches that ASIC directly to a charge module. And I'm looking to characterize the ASIC performance in liquid xenon, develop procedures and find out what challenges will occur in the coming years when we start to build Nexo, and also explore sources of external noise that we may not have been expecting. There's a candidate ASIC for the Nexo charge readout called the Cryo ASIC out of Slack. And this team on the bottom left, electronics team, is really great. They've developed this ASIC over a number of years. It's also being used for Dune, slight variations, but it's a system on chip waveform digitization system. It has an analog front end, which is a charge preamplifier on the chip. It's got programmable gain and peaking time. There are ADC blocks that are 12-bit differential ADCs that total 64 channels on a single chip. Data, this is pretty impressive. Data needs to be streamed out very fast these days, and this chip can do about a gigabit per second serialization and data transfer. So that's a big challenge with integration. How do you retain that high-speed data transfer? And also, they like to advertise that the power is configurable. The total power burned by this chip is configurable because you can turn on and off different blocks of the chip. There's on-chip regulation that's configurable, which is pretty impressive. The top right diagram shows the analog front end. It's a charge preamplifier with some filtering, and actually it's really measuring the current. So as opposed to having a long time constant where you have a plateau at the top, this is on the left simulating what charge collection responses would look like, and they're pulses. The chip has configurable peaking times, so you can change the width of this pulse, and the integral will equal the charge. So this work is really dedicated towards testing the electronics in the liquid xenon. And I mentioned this, the charge tile readout on radio pure quartz substrate. It's actually quite hard to fabricate. Those strip crossings are difficult to fabricate, and wrapping the signals around to the backside is difficult. So I want to decouple the effort of fabricating the tiles from the effort of testing the electronics. So we built a 4-layer PCB made out of ceramic, which is an industrial process, which you can just go and order these boards, that mimics the Nexo charge tile geometry. It's electrically topologically the same, because on the internal layers, you can gang these pads up in the cross strip pattern pretty trivially. So this is what the test tile looks like for this effort. And on the back, there's a high fire that looks blue. The strips have vias that wrap around and terminate here, where wire bonds can be made. Next one needs a board to house the ASIC to distribute all of those data lines and power. And that's what this orange board is. It's orange because it's made out of polyamide. So this may not be possible for Nexo to use polyamide 8-layer PCBs because there's some outgassing to consider, but our Stanford test stands, we can afford a little bit of impurity. But this is sort of what it looks like. At the edge of these boards is where the tile strips make contact with the board and are routed to the inputs in the ASIC. So a zoom in here shows these pads on the blue, where the tile strips that are wire bonded to these fingers. And one challenge if you're integrating a board system like this is to think about how you're actually going to attach this to this delicate ceramic board. I need the wire bonds that will bridge this gap to not be moving at all under some thermal stress. So they need to be hard bonded. But at the same time, there's a thermal coefficient of expansion mismatch between the kapton and the ceramic. So one can't have that introduce shear forces on the glue, for example, to debond this board entirely. So that's what this funny finger and knuckle pattern is, what I call the finger and knuckles. So when the kapton and ceramic stretch relative to each other, the fingers are held in place so that the wire bonds aren't moving, but the energy due to the mismatch is stored like a spring in the knuckle region. And this is the idea behind this pattern. We have yet to demonstrate that this won't fall apart, but we think that it'll do okay. Here's a few pictures of the assembly process, me putting on these ceramic spacers, which sort of lift the board off of the surface of the tile. here's applying low outgassing master bond epoxy that's been used in some other experiments to each of these fingers, and then placing the board on these standoffs. The next step is to bond the ASIC to the board, and that's been done and studied by Sander Brouwer and Chris Kenny's lab at SLAC. So I'd like to thank them, and they're really good at that. After one bonds the chip to the board, we took it to a commercial wire bonder in San Jose, which I'm thankful for their flexibility of wire bonding this sort of strange object, and it turns out looking beautiful. So completely wire bonded both at the edges and the chip. To control the ASIC, one needs some system of boards that translate computer commands to commands to the ASIC. So SLAC has developed some general purpose FPGA boards for doing so, and some specific purpose boards that do exactly the level shifting and translation needed to talk to the ASIC. So computer talks to these boards via optical link. And then at the other end of this, all of the lines are funneled into two sub-D25 cable formats that go to the xenon space. We need something that's compatible with conflat feed throughs. SLAC has also done an amazing job at developing a software suite to control ASICs, and the software is intimately tied to the firmware. It has a graphical user interface, which I'd like to emphasize because it's very user-friendly. Here's a sort of a video of some pulses coming in and triggering events at 1 hertz. I'm mentioning here that SLAC has a test bench with a non-cryogenic compatible board, non-xenon compatible board with an ASIC on it that's demonstrated independently that the ASIC works well. So this is data from that test bench, and we are moving towards putting the ASIC into a liquid xenon TPC. So this is sort of a diagram, cartoon of that setup where things are a little bit more complex than on the bench. There's a lot of cables. There are a number of feed throughs that eventually lead into a liquid xenon space where that Kapton-based board is. And one place I'd like to improve after learning with this system is that it's a little hard to scale to more tiles. So next step would be to have, say, 4 tiles, and that's going to be quite complex if we continue to use this many feed through, many cable configuration. So I'm trying to learn how to simplify this picture a bit. But that'll come in the following. Thank you. I'm actually just going to conclude here. So at the present moment, we're currently testing the data transfer lines, the high speed and the slow controls lines on the bench with these cold boards. I'd like to demonstrate the cold boards and ASIC work on the bench. SLAC already has that demonstration with some non-xenon compatible boards. So we know the ASIC works, just got to test these new boards. The liquid xenon chambers we operate at Stanford on a regular basis. I operate them, so they are ready to for a test whenever these electronics prove that they can operate on the bench. And a few goals here are sort of repeating, but I'm really looking forward to characterizing the performance of the ASIC in xenon and analyzing how this affects our prospects for neutrino subbeta decay detection. So thank you. I'll leave it there and open up for questions.
Thank you, Evan. We have time for one quick question, if someone has one. And Vincent Bass, you're up next if you want to get ready. Okay, great. Let's go ahead and get Vincent queued up. Thank you very much, Evan.
And you can see the slide moving. Oops.
We've got you. You're good to go.
Perfect. All right. Yeah. So I'm Vincent. Today I'll be talking about the SBND Photon Detection System. Just a quick reminder what SBND is. SBND is the short baseline detector that is part of the short baseline neutrino program at Fermilab to look for a probe oscillation with a delta m squared that's equivalent to about 1 eV squared, which was Minnie Boone saw. So SBND is really uniquely placed. It was placed just about 100 meters from the target, means that it can do very interesting physics. And SBND is currently under construction, so this is just a mock-up design of the TPC that will be placed into the cryostat. So the main purpose of SBND will be to measure the unoscillated flux of neutrino that comes from the BNB, the boosted neutrino beam. and that's for the SBN. And that's really crucial because the Icarus detector, which we place further along the beamline, will be a LRTPC as well. So having a near and far detector using the same technology and target can make us control a systematic much easier. But at the same time, because SBND is so close to the target, it will essentially become one of the world's largest high statistics cross-section on argon, liquid argon, with about 7 million new mu interaction in 3 years of running, including about 50,000 new interactions. So that what allows us to do, it will allow us to precision measurement on exclusive event topologies. And on the right side, I'm just giving 2 examples for the new mu here, inclusive. But when you start going to exclusive channels, you see that we can probe quite significantly a lot of the channels for new mu charge interaction. But at the same time, it will also be able to perform some BSM physics. This is just 3 type of things that we'll be able to do: some dark matter, neutrino trident, and even some heavy neutral leptons. So SBND is going to be a LRTPC. So it's quite a big TPC, 4x4x5. It's actually it will consist of 2 drift regions, which will be divided by a central cathode in the middle. So you see both anodes on each side, which are made of just about 11,000 wires. And then in the middle, we'll have the cathode. And this is just an example. This is a picture of one of the wire planes that essentially is ready to be installed. But what's more interesting for this conference especially, and what I'll be concentrating on, is really the photon detection system. SBND will have quite a unique photon detection system. The baseline will be 128 inches Hamamatsu PMTs, which we can see in the 5 dice layout in this PDX box here, but it'll also have 192 XR Puka, both visible and UV light detection. You'll see what I mean in just a bit, and it'll be just placed in between the PMTs. The other thing, what I call a passive element, is that the cathode will be mounted with wavelength shifting reflecting plates. So you can see here just a big reflector that we evaporated TPB on it. So the whole cathode will be covered in this. And why are we covering the cathode? Is because all the light that would generally go towards the cathode, we would normally lose it. So you can think of a normal TPC that has an opaque cathode would have the blue trend that we see here. So as you go away from the photon detection system, your light yield goes down. But as the cathode is covered, now you gain back this light that we normally lost. It will be wavelength shifted, but you'll be able still to gain it. So then you get a higher and a more uniform light yield across your full detector. So the plates, what they look like, this is I showed a quick example before. We have the plate, we evaporate TPV on it. We get these plates here. We make 64 of them, double-sided. And then this is a picture of them being installed. So each of the 16 windows have 4 panels, and they're sandwiched with metal mesh to make sure that we keep a constant electrical field. So as of recently, all these 16 panels have been assembled, and they have been installed on the CPA right here. The reason why we can't see them, obviously, is because they're light sensitive, and they'll be spending quite a bit of time while the rest of the TPC is being constructed. So we're just protecting them with these quite large plastic, thick plastic covers. There we go. So the first active element are the PMTs. And the first thing you'll notice in this picture is that you can see 2 different types of colors when you look at the PMTs. And this is because 96 of them are TPB coated, and you can clearly see which one they're more bluish, if you want, the one that are TPB covered, while the uncoated are darker color here. And actually, this is a picture of the SBND PMTs being tested in the CCM detector. And there's actually a paper, if you're interested, about the performance and as well as first physics result using these PMTs. Currently, all the PMTs are now at Fermilab. This is them arriving in one of those PDS box, so it's properly shielded, and they're currently just waiting to be installed in a in a blue and UV protected room and also covered in tarp. So the other active element is the XR puka. There were a talk a couple of days ago and a poster on more on this. I'll just quickly go over overview on it. But what's really important is that there'll be 192 module. 176 will be using these SIPMs here, while 16 will be using another type of SIPMs here. So we'll be able to compare the performance of each. And like the PMT, we'll have, this will be divided in two. So we'll have about 88 that will be sensitive to UV light and one that will be sensitive to the visible light. And this is just an example of one of the XR puka module being tested in a small door. And this, all of them have been assembled already. So the module are all ready to go essentially. This is just a photographic process of how it's going. You know, you start with the screws, you start to build the actual module itself. We put the filter, we put the wave, the light guide, then we put the back that has a reflective surface. And these are currently at Fermilab and they're waiting to have the SIPMs be installed. So just to give it like a cartoon shape of what this will look like, and this is kind of what it will look like here. So each of the 12 windows have 5 PMTs and 4 sets of double XR puka, which one will be sensitive to both the UV light and the visible light, and one will be only sensitive to the visible light. And then here's another cartoon just to give an idea. If you had an event somewhere in your TPC, some of the light will go directly towards your PDS system. Some might be going to the cathode, which can be reflected, and then you'll have different combination of the light that you'll see depending on where you are and if the light bounces off and on which sensitive PDS it goes to. So this is an example of one of the real boxes. So doesn't have the XR puka mounted on already, but you can see clearly what it will look like. And this is just an example of a mock one that we had, which was just to test essentially that we have enough space in the back to install the XR puka here. So soon enough, we'll have our 4 couple of XR puka being placed in the PDX box. Another thing that we'll have is a calibration system. So it's a series of diffusers that will place on the cathode that will be facing directly towards the PDS system. We'll have 5 of them. They have been installed. It's a bit of a low quality picture because we had to zoom in, but this is the diffuser system right here. And we'll have a fiber optic cable coming in that will come from the top to go inside the diffuser. And then the diffuser itself will diffuse the light. So the fiber will connect it to this laser that we see right here to produce 2 wavelength, 213 and 532, to give a UV example and a more of a visible light sample of the light, so we can perform the 2 calibrations. So just in summary, I hope I convinced you that SBND will have one of the most versatile photon detection system with quite a large coverage compared to currently running similar detector. One novel thing that we'll have is we'll be able to distinguish between visible and UV light, and what it will allow us is really to perform a drift position determination just by looking at light, because depending on where you are in the drift direction, you'll have more UV light or more reflected light from the cathode. And at the same time, we'll have quite a significantly increased light yield, which will definitely help us in cosmic rejection, because we'll be able to set a higher threshold. And there's hope as well that we can do some calorimetry using the light only, as that also improves energy resolution. So the cathode reflective plates have been placed just last month. So this is all done. All the PMTs are at Fermilab. They've been tested once they got here and they're ready to go. The XR puka system is entering the final phase of assembly. You've heard that all the SIPMs using the Daphne readout have been tested. So now we're currently cabling all of them together, and soon we'll be able to place them in the box. And then at the same time, its PC construction is underway. And in here, I'm just leaving you with 2 nice pictures. So this is the building. So the cryo system, you can see the cryo system in the back and in the outside, and some on the inside there. And you have the cryostat being currently installed. And that's it. Thank you.
Fantastic. Thank you very much, Vincent, for that great overview of this system. Any questions? We have time for a few. I have one. Can you remind us what sort of, I guess, position resolution this number of channels, optical channels you have will offer you using just the light detection system alone?
Yeah. So we're actually currently updating the studies now that we have a final layout of what will be where. And if the number on top of my head is like tens of centimeters, I believe, probably close to half a meter. But that is quite good if you just think to do it on the fly without any charge information. So we'll be able to do, if you want a preliminary position resolution, to try to locate where the event is as the data is being taken without having to perform the whole reconstruction, which would take quite some time. But we're still trying to understand what kind of resolution we can get as we are updating our simulation.
Cool. Fantastic. Okay. If there are any other questions, we have just a moment. Ines, I see you're up next if you want to prepare. And well, if there's no hands going up, then why don't you take it away?
Yeah, can you hear me?
We can hear you and see your slides.
Perfect. So good evening. This is Ines Gil Botella from CIEMAT, Spain. I'm going to present the scintillation light detection in the 6-meter drift length protodune dual phase liquid argon TPC on behalf of the DUNE collaboration. So deep in the ground neutrino experiment aims at answering fundamental questions by performing precision measurements of the neutrino oscillation parameters, nucleon decay and other beyond the standard model searches, and detecting supernova neutrinos. DUNE is located in the US and will consist of a new neutrino beam facility at Fermilab and a highly capable near detector to measure the unoscillating neutrino spectrum and constrain flags. And 4 times 17 kiloton liquid argon TPC modules, which will be placed underground at surf 1,300 kilometers away from the neutrino source. As a previous step, and due to the complexity of the detectors and the infrastructure, the DUNE program is running at the CERN neutrino platform right now. So the goal is to build and operate one kiloton scale prototypes, which is really a critical step to demonstrate the liquid argon TPC technology at these large scales. So there are 2 prototypes, as you know. One is single phase, where the drift is horizontal along 3.6 meters. And the other one is protodune dual phase. In this case, the charges drift vertically along 6 meters, and then the charge is amplified at the gas phase. So this is a picture of the protodune dual phase, has an active volume of 6 times 6 times 6 cubic meters, and this is the largest dual phase liquid argon TPC ever operated. The scintillation light is detected by a photon detection system form of photomultipliers that are placed at the bottom of the detector that you see here. And this is a inner view of the cryostat with a high field gauge, the charge readout planes, the cathode, and all the elements. We also installed 2 cosmic ray taggers to the external walls of the cryostat to trigger on muon tracks passing through both CRTs. Protodune dual phase took data, cosmic muon data from 2019 to 2020, and the operation faced some issues that impact the TPC field conditions and affected mainly the charge readout. This is a picture of the details of the PDS at this form, as I said, of 36 8-inch cryogenic PMTs. And we use 2 different wavelength shifters at this in this detector, PEN and TPV, to shift the UV light, as I will comment later. And also we install a light calibration system with a fiber end pointing to each PMT to calibrate and compute the gain. And also we use an external DAQ system, a dedicated light acquisition software. And here you see the links to the publications that we have prepared for the different components. So protodium dual phase PDS collected cosmic ray data for 18 months. It operated with a detector fully filled with liquid argon from August 2019 until May 2020, when the liquid argon started to evaporate in preparation for an intervention on the high voltage system that took place in June. Then in July, the detector was refilled using the xenon doped liquid argon from protodium single phase, which was contaminated with nitrogen. And in August, operations were resumed and 2 additional nitrogen injections took place to measure the effect in the light attenuation length. And you can see here the different concentrations. The PDS has operated really in stable conditions all the time. And as I said, we took data with these different liquid conditions and also with different trigger modes that were very useful in order to identify different kind of events. So we used PMT trigger, which provides PMT signals in coincidence over a given threshold. We also took data with a CRT trigger, allowing to record single tracks with known topologies, of course, calibration and also random trigger modes. So we took more than 130 million of events during almost 700 hours. And here I can show you one picture of what we call one event, which contains the information of the 36 waveforms. And we measure the time accuracy among the PMTs for the same event, being better than 16 nanoseconds, which is the sampling time of our IDC. And we also measured a remarkable low noise in the baseline, 0.68 DC count. Here you see a single photoelectron waveform at a gain of 10 to the 7. And also we measured the single photoelectron as a function of the gain and with a very good signal to noise ratio larger than 11 for this gain. The PMTs were calibrated weekly because they were switched on and off to allow the cameras and the LEDs being operated. And in the figure, we show the gain evolution for all the PMTs during 1 year of operation. And even that, as I said, we needed to switch on and off every day. PMT gains were very stable with time, with standard deviation around 9%. As I said before, 2 wavelength shifting methods have been used in protodium dual phase. Pen foils installed on top of the PMTs, as you can see here, and also TPV coated PMTs. And we measure the relative photon detection efficiency of the pen PMTs versus the TPV PMTs. And we detect that, this is the factor that we obtained. That means that as a result, the TPV PMTs detect 4 times more photons than pen PMTs. And taking into account the geometrical differences between both systems, we computed that, we estimated that the TPV will produces actually 3 times more visible photons than pen. So we have proven really that the light detection with the pen foils is possible in a very large liquid argon TPC for the first time, and also they can be used as an alternative to the TPV wave shifting. So we have also studied the liquid argon scintillation time profile for muon-like events with no drift, and we have generated this kind of average waveforms with the time profile. So this was described with as the sum of 3 exponential decays convoluted with a Gaussian to represent the detector response. So these are the 3 times that we have used. So the fast component was fixed to 6 nanoseconds, and then we studied the slow component as a function of the time, as you see here. So we have measured that to be 1.45 microseconds. That was monitored regularly, and indicating that the liquid argon purity was very high at the level of the PPV. Although the scintillation time profile should be in principle explained by only these 2 components, we added one intermediate component to allow the fit to converge, as reported also by other liquid argon experiments. And we clearly see here the difference between the 2 different wavelength shifting PMTs. pointing really to a delay emission time by the Williams shifting material. We also developed a dedicated simulation to compare data with Monte Carlo for cosmic muon light produced in the protodune dual phase. Simulation of these cosmic induced particles is based on Corsica, and we developed a full simulation of the geometry. And also we use these values for the photon propagation in liquid argon, but also we tested other values as alternatives to compare with our data. We generated photon libraries. And here in the plots, you can see top and side views of maps with the detected photons per voxel, which are the cubes of this size, per deposited MEV across the volume. So now I'm going to show you how this Monte Carlo compares with the cosmic data. For that, we used the CRT trigger events because we know the topology of the tracks. And here in this plot, you can see the primary S1 charge detected by each PMT in a top view for data in Monte Carlo. And you see that the patterns fairly reproduce the expected gradient. So PMTs really closer to the bottom CRTs detect more light than the other ones as expected. And here we also study the correlation between the S1 signal and the distance from the track to the PMT. And this is for data, this is for Monte Carlo. You see that we can detect perfectly well the light up to 5 meters. And after that, beyond that point, light is detected, but low energy background dominates, and this is not reproduced in the Monte Carlo as you see. However, the data Monte Carlo match within 10%. We also studied the suppression of the electron-ion recombination process due to the drift field. And so this implies the reduction of the primary scintillation light production and then the light detected by the PMTs. And this is shown in this plot where the charge versus distance distributions for no drift field in black is compared with the case of the cathode at 50 kilovolts in red this is the ratio of both. And this ratio corresponds to 17%, at least 17% of the scintillation light detected in absence of the drift field comes from really the electron-ion recombination. So if we consider an average drift field, because in the case of the protodune, due to the short circuit at the high voltage extender, the drift field was limited just to a few meters from the top. If we consider an average drift field of 0.09 kilovolts per centimeter, this is the point that we can add in this S1 versus drift field, and also the comparison with other experiments. We also observe a decrease of the slow time component, as you can see here, as a function of the cathode voltage, as was also reported by the 3x1x1 cubic meter dual phase liquid argon demonstrator in this publication. And also in this other publication, they pointed that this could be due to the quenching of the long-lived triple states through the self-interactions with other triple states or through the interaction with molecular argon ions. So this is a clear observation also in protodune dual phase. Protodune dual phase, as I said, because it's the longest drift distant liquid argon TPC ever operated, may allow to develop unprecedented studies on the light propagation. And this is what we have tried here to evaluate the Rayleigh scattering length. And here you can see our data compared with two kinds of Monte Carlo when we used the published Rayleigh scattering lengths of around 1 meter and 61 centimeters to compare. And as you can see, the agreement between the data and the 1 meter Monte Carlo sample is better than with the short one. And also the table shows the attenuation length from the previous feeds. And we see also the good agreement between the Monte Carlo of 1 meter and the data. So this measured attenuation length means that the light undergoes Rayleigh scattering before being attenuated due to, for example, liquid impurities, absorption layer on detector or on detector elements. And this is achieved thanks to the excellent liquid argon purity that we had. Also, we studied the effect of the UV reflections in the different detector materials on this. And then we concluded that at least 11% of the light detected by PNTs comes from reflected UV light in aluminum or stainless steel. This is an example, another result. We have many results from protodion dual phase. Here, this is an event where we observe the electroluminescence signals, so the secondary scintillation signals produced in the gas phase due to the extraction and amplification of the drifted electrons in all the 36 PNTs, and the light is coming from 7 meters away from the PNTs. So this shows that the system is quite efficient. And we have measured also the single photoelectron rate without the effect of the field. It was we went from kilohertz to megahertz when we switch on the field, and this is due to the presence of the S2 signals. S2 also provides information, of course, of the drifted electrons, but protodion dual phase has some limitations. So this is an example of the S2 signal after the S1 signal, and then the signal duration is around 2 milliseconds, which is quite consistent with expectations for a field of 0.2 kilovolts per centimeter, as we reported. My final results are related to the xenon doping in liquid argon TPCs. As you know, the use of the xenon doped liquid argon is a very promising alternative to the pure liquid argon for large-scale liquid argon TPCs, since it really mitigates the light suppression due to the impurities and also improves the photon detection efficiency and uniformity. And this is shown from data of protodion dual phase. In the figure, we see the variation of the signal amplitude and the total primary scintillation light for 4 different doping conditions, as I explained at the beginning, relative to the, of course, to the pure liquid argon. Black dots represent the PMT trigger events, so events that happen close to the PMTs, and the red squares correspond to the CRT trigger events, which are tracks between 3 and 5 meters away from the PMTs. And what we observe is that adding xenon, as suspected, we observe a clear reduction of the S1 amplitude. The fast component is reduced around 35% for both triggers due to the absorption of the 127 nanometer photons by xenon and also nitrogen. And at the same time, we clearly see the large increase of the collected light. We observe 50% total charge increase for the near tracks, while 100% has increased for far tracks. And this is understood because of the improved uniformity for the 178 nanometer photons. Adding xenon, what happens? Well, we expected a reduction of around 15% according to this paper on the amplitude, the fast component. However, we do not observe this reduction. For us, the fast component remains constant for both triggers as adding the nitrogen. So this is flat. What we
1 minute, Inés.
Yeah, thank you. So we clearly observe is a reduction of the charge due to the argon-argon and argon-xenon quenching, and this is observed in both triggers. Total charge is reduced around 30% independently of the distance. So it's a process that is not coming from the propagation, but from the production point of view. We are studying the time profile of the xenon doping liquid argon light. And we clearly see that the time profile with pure argon is black, the black curve. And as soon as we add small amount of xenon, we go to this red curve, and then we see the other curves when adding more xenon and also in the reduction due to the nitrogen. So the bump, of course, is due to the late light at 150, 178 nanometers. And as I said, due to the nitrogen quenching, this bump changes. And we feed the waveform to the sum of 3 exponential with a Gaussian. And this is the feed that we have. Dots are our data as a function of the xenon and the nitrogen concentration. And it fits well with the model that we have developed in order to understand this light production. So I go with the conclusions. So the liquid argon TPC technology at large scale is being demonstrated in the ProtoDune program at the CERN neutrino platform. And this is very important for the future Dune long baseline experiment. ProtoDune dual phase operated in 2019-2020 at CERN with limited field conditions. However, the photon detection system collected very nice cosmic ray data for 18 months in very stable conditions with all 36 PNTs being operative. And this validated the system design for long drift liquid argon TPCs. We have used for the first time the pen as the baseline on our PNTs as a wavelength shifter in a very large liquid argon TPC. And we have measured their wavelength shifting efficiency compared to TPE. We have observed also the light suppression due to the drift field, due to the recombination, and also the decrease of the slow time constant. And we have also developed some studies on the light propagation for the Rayleigh scattering. We have observed the electroluminescence signal from 7 meters in all the PMPs, also showing a high detection efficiency. And I must say also that the ProtoDune dual phase has demonstrated the improvement of the light detection efficiency and uniformity in large liquid argon TPCs due to the xenon doping, even in presence of nitrogen impurities, which is also, as I said, very important for future long drift liquid argon TPCs. That's all. Thank you.
Thank you so much, Inés. I haven't seen any hands shoot up, so perhaps any questions that pop up can be posted in the chat. Tommaso, if you're up and ready to go, that'd be great. Thanks, yeah. Inés, again. We'll look forward to the publication on that. What's the timeline for that, do you think?
The publication is now under review by the collaboration.
So a few months maybe or something, yeah, for the archive post? Okay, awesome. All right, Tommaso. Are you with it? No, oh, you're muted. There we go. Now we can hear you. And you should be able to share your screen.
My screen, yes. So here we are.
And we see your presentation, your PowerPoint.
Okay, perfect. So I'm going to start.
Okay, you're good.
Okay. Thank you. So my name is Tommaso Gianmaria, and I'm a PhD student of the University of Ferrara. And in this talk, I'm going to discuss the characterization of the Dune photodetectors and study of the event first burst phenomenon. Dune is a leading neutrino physics experiment that will answer some of the most compelling questions in particle physics and cosmology. It will have a broad band neutrino beam traveling through the longest baseline so far used for an accelerator neutrino experiment. The aims of this worldwide project are the measurement of the CP vibrating phase, the neutrino flavor mixing angle, and the mass ordering. It will also study the supernova neutrino bursts and the possibility of proton decay. The Dune Far detector, where the bulk of its vast scientific program will be covered, is made of 4 liquid argon time projection chambers, and these technologies are currently prototyping at CERN in the ProtoDune experiment. The current general plan contains a high number of upgrades on TPC technology, for example, a larger active volume, a new dual phase design, a vertical drift layout proposal, a new PCB anode plane structure, and many others. Some of the topics were mentioned in other presentations and posters in this conference, like the previous one of Inés about the dual phase design, and the talk, for example, of Sabrina about the vertical drift layout. Among these, the integration of new generation photodetectors is of high interest. In fact, modern silicon photomultiplier models will be employed to detect light produced by charged particles interacting with argon. The choice of employed solid-state photodetectors stems from their high sensitivity and dynamic range, as well as the possibility to cover large surfaces with high granularity. In ProtoDune 2 single phase, this sensor will be massively employed in the photodetection system, and the CPMs will be placed inside the X-Arapuca modules in the so-called supercells, placed in a horizontal line along the APA frames, with one cold amplifier that handles signal from every 4 supercells. The CPM, also called multi-pixel proportional counters, are solid-state photosensors capable of detecting single photons. The basic design, common for different models, is a matrix of single photon avalanche diodes, SPADs. And with respect to the older photosensors, CPMs are characterized by good robustness, magnetic field immunity, high sensitivity and dynamic range, and reduced cost and size. In general, all the contribution to the CPM signals that are independent on the incident light intensity are enclosed in the dark count rate definition. The DCR is a background signal happening also in absolute darkness, and for this reason, it is the main drawback for low photon count application like DUNIS. The issue of high DCR can be overcome by lowering the CPM's temperature down to cryogenic level, with the result of reducing the DCR value to tens of millihertz per millimeter squared. An international consortium of research groups is currently engaged in a systematic comparison of the performances of the CPM models that have been custom designed for DUNE by two manufacturers, the Fondazione Bruno Kessler and Hamamatsu Photonics. This talk, presented on behalf of the DUNE Photosensor Group, is an incomplete summary of the work done by the group until now and currently going on to fully characterize and test these CPMs at liquid nitrogen temperature. The aim is to select the best choice for the DUNE photo detection system, as well as characterize the response of the chosen detectors for the DUNE simulation. The groups received 4 different CPM models to be fully characterized one by one in the first part of the general procedure. As shown in this table, the models differ from cell size, number of cell, packaging, and design. And this first characterization is already finished, with the resulting parameters being well within in the DUNE specifications. And the best candidates for the down selection mentioned before are highlighted in bold in the table. The second step is to perform the so-called ganging test, that is the characterization of boards containing 6 CPMs each. And the second test was also successfully completed this year, while the final test, which is a high number, around 8,000 units, will be tested, is currently going on. The inherent complexity of having such several samples raised the need of developing custom experimental setups and procedures to speed up the characterization process. With these upgrades, the labs involved in the test foresee to perform around 120 CPM characterization per day. The main parameters involved in the CPM characterization are listed here, and in order to characterize the CPM detectors, the first step consists in the measurement of the IV curve, which allows to extrapolate the breakdown voltage and the quenching resistance. We perform this procedure first at room temperature to check the info from the vendors, and then at liquid nitrogen temperature to set the working point for other measurements. Breakdown voltage is evaluated as the maximum of this function, while the quenching resistance is the slope of the linear part of the forward region, that was the reverse region. Once the breakdown voltage and quenching resistance are determined, the second step is to count the signal produced by the CPMs, with applied voltage that exceeds the breakdown voltage by a few volts and in absolute darkness to get the DCR, CT, and AP, so dark count after pulse probability and crosstalk probabilities, from the time versus amplitude distribution of events. Since we expect rates below the 100 millihertz per millimeter square at half photoelectron threshold, the light screening and the electronic noise reduction were particularly challenging for this task. Lastly, the gain and the signal-to-noise ratio can be extrapolated from the amplitude distribution of the recorded events with an LED acquisition that I will explain in this slide. A large aperture viewer placed into a custom dark box and filled with liquid nitrogen provides an adequate environment for the measurement. And this dark box is covered with polyurethane-coated black fabric to shield the sensor from external light. And the characterization of the CPM starts 30 minutes after the immersion in liquid nitrogen to ensure the full thermalization of the sensor. The instrumentation used for the IV curve is a semiconductor analyzer, or equivalently a standard source meter with nanoampere precision, while for the DCR, for that noise characterization, we use a custom apparatus based on cryogenic AC amplifier and a high-performance oscilloscope. For the gain and the signal-to-noise ratio measurement, we follow procedures similar to the DCR measurement, but with the CPM placed in front of a LED, and the acquisition is triggered by the LED pulse. In this way, we will populate the high amplitude events and get more precise estimation of gain and SNR as a function of the overall voltage. All these tests were done at liquid nitrogen temperature before and after 20 thermal cycles to check the resilience of the to thermal stress. The groups of the photosensors section developed a custom algorithm to perform the offline analysis with the common purpose of extrapolating DCR, CT, and AP values. And this is done from the raw data of the oscilloscope. This is done in 2 steps. The first one is the isolation of the single peak signals in order to compute the relative time to the beginning of the acquisition and the amplitude by subtracting the local waveform baseline. And the list of selected peaks is then processed to extrapolate dark counts, CT and AP, by incrementing counters following a simple Boolean rules and producing the relative plots. One of these is this one. This is the distribution of selected events in terms of peak amplitude and time delay. This is a simple time distribution, and this is time amplitude versus time. And here we can see, we can distinguish a cluster of events with 1 photoelectron amplitude and delta T of the order of a second, which is the primary DCR. Then same amplitude, but smaller times for the after pulses, and amplitude of 2 photoelectrons or more for the crosstalks. But there is also another contribution. There is a group of events of 1 photoelectron amplitude and with a delta T of the order of 0.1 to 10 milliseconds, 0.1 to 10 milliseconds. And these events correspond to quick trains or bursts of events, correlated events, the origin of which is still to be understood, but is under study. The presence of the burst is clearly visible also in the time trend distribution of the events, which is an histogram displaying per each event the time interval between the current peak and the previously recorded peak. We observed the burst in many of the tested CPMs, and the randomness of this behavior brings the DCR to different values, even when repeating the measurements on the same CPM. This randomness raised the need of a new burst-independent parameter to compare performances of different CPM models in terms of dark noise. This parameter is nothing more than the standard DCR, but we have somehow to drop out the burst contribution. In order to do this, we developed 2 analysis tools, which will be referred as the tag method and the fit method in the following slides. The tag method is used to isolate the burst event one by one. In this way, we can remove their contribution to the DCR value. This method is based on finding consecutive events with short time delay between them, putting an upper limit to this time, Tmax, and also a lower limit in order to distinguish them from the after pulses. This distinguishment is enforced also by the number of consecutive events, which has to be larger than a typical threshold, typical set to 5. Best values for the burst identifications were found by tuning these parameters to catch all bursts, checking on several sets of data. The fit method is both conceptually and practically different, as it identifies the standard DCR cluster from the burst contribution directly from the delta T distribution of events. In fact, it relies on a fit on the histogram shown in figure. The functions used are a Poissonian distribution for the uncorrelated DCR events and an over-dispersed Poissonian for the burst contribution. In order to cross-check the validity of the 2 methods, we compared the results in terms of DCR, which are in agreement with each other. Furthermore, we can distinguish different properties of these 2 algorithms. Since the fit method relies on a direct fit on the histogram, it furnishes a fast way to discriminate DCR from burst, especially important when dealing with high number of events. On the other hand, the tag method scans all events one by one, so it can be used to analyze and eventually extract some common features of single events within the burst. Some of these features that we have found are that the bursts tend to start with a relatively high amplitude event, often more than 4 photoelectrons. The average number of events in a burst is around 100, and delta T are around 0.5 to 10 milliseconds. and they generally last for a few tenths of a second. As I already mentioned, the values of the measured DCR differs from different models of CPMs and seems to be randomly distributed, while the ones calculated after eliminating the burst contribution are more in agreement with each other. Here in the figure, there is the same plot in slide 10, and on the right side, there is the same plot, but performed after the burst removal with the tag method in this case. And we can see that the burst contribution is no longer present. Concluding,
oh, great.
Yeah, perfect. Concluding, in this talk, I presented a brief description of the ProtoDune 2 single-phase photo detection system, which is based on the CPMs and presented a summary of the work done by SPPD group to characterize these sensors. We developed custom experimental setups to accomplish the full characterization of samples, of all the samples at cryogenic temperature. And the results are well within the Dune specifications. The DCR is in general higher than the expected values due to the burst phenomenon, but we developed some tools to eliminate the burst contribution from the dark counts. The last of the three characterization steps mentioned before, the mass test, is currently going on. And in the meanwhile, we developed some tools to isolate and study the burst. And we have identified some common features that were listed in the slide before. And currently, we are investigating this burst phenomenon with dedicated studies and in collaboration with the vendors. Okay, I have finished.
Great, thank you so much, Tommaso. This is really good work. Perhaps you can, Tanya, I see you have a question. Perhaps you can post it in the chat because we do need to move to the next speaker, Haikam, who is connected. Yes, please.
Okay. Oh, I lost the conversation. Sorry. Okay. I think
there we go. Okay. And so Haikam, we've got you. If you can share your screen. And we've got you. You're ready to go.
Can you see my screen? Can you hear me?
Yes, you're good.
Okay, all good. Hello, everyone. So my name is Isham, and today I'm going to make a presentation on the characterization of parine films for background rejection in liquid argon dark matter experiments. So this study has been carried out at Queen's University within the DEEP collaboration. So first, the DEEP 3600 experiment. It's a dark matter direct detection experiment located at Snow Lab in Ontario, Canada. It's located 2 kilometers underground, which allows to greatly reduce cosmic and atmospheric backgrounds. So the geometry of the detector is shown here. So we have an acrylic vessel filled with liquid argon at 87 Kelvin and coated with a wavelength shifter, TPB, on the side. The interaction between WIMP and an argon nucleus will lead to a UV scintillation that is wavelength shifted thanks to the TPB before being detected by the surrounding 255 photon multiplier tubes. So the DEEP experiment is very sensitive, but there are many sources of background. A few of them are alpha decays from radon progeny, beta decays from argon isotopes, also gamma rays and neutrons from the glass of the PMDs. In the DEEP experiment, the pulse shape discrimination is carried out thanks to the prompt fraction, which is an indicator which is a ratio of number of photoelectrons detected in a short window, a few nanoseconds, over the number of photoelectrons detected in a longer 10 microseconds window. That prompt fraction allows to distinguish two types of events. Electronic recoil events, where an important part of the light is in the later parts of the pulse, with lower prone fraction, and mostly background events, and nuclear recoil events, for which most of the light is included in a short window, and which is actually the signal of interest for us, as the WIMP is expected to nuclear recoil with the argon nucleus. So this PS, this pulsar discrimination, separates these electronic backgrounds from the nuclear recoils with very good efficiency. And as you can see here, most alpha backgrounds, which are nuclear recoils, have energy that are high enough to be discriminated from WIMP signals, for which we expect only a few hundred photoelectrons. However, if these alpha events occurs in the neck of the detector, it produces scintillation light that is shadowed by the surrounding acrylic. And that creates an artificial low energy event that mimics a WIMP-like signal. So what you can see here is what's happening right now in the detector. An alpha event leads to this pulse shape. And this is very close to what we would expect for a WIMP signal. And as you can see here, this is the dominant background in the region of interest for WIMPs. So you can see the number of events from various types of background in the WIMP region of interest. Electronic recoils, which are very well mitigated, neutrons, and also alphas. And you see the most problematic backgrounds are those alphas in the neck of the detector. And this is the limiting background for the WIMP sensitivity. To mitigate this problem, an idea is to add a coating of a long time constant scintillator on the neck of the detector. This coating is here represented in blue. The idea is that the light emitted by an alpha event in the neck will be wavelength shifted by this long time constant coating, and will be easily discriminated because of its reduced prone fraction. An idea for this long time constant scintillator is pyrene. So we're going to see here if that could be a good candidate. So what we've carried out at Queen's is trying to understand a little better pyrene. However, pyrene has low vapor pressure, so pure pyrene is not suitable. An idea is to use pyrene embedded in a polystyrene matrix. Our objective at Queen's is to understand the pyrene polystyrene fluorescence at liquid argon temperature in particular, through three main aspects: wavelength spectra, fluorescence yields, and finally fluorescence decay time. And our main asset is a cryogenic facility, which has a good optical efficiency and allows us to reach a very low temperature, around 4 kelvins. So here is a little presentation of the setup. You can find more details of the experimental setup in Emma Lingwood's talk. We studied 4 different pyrene samples with varying concentrations in pyrene, 12%, 15%, and various fluorescence grades, which is, to simplify, an equivalent of purity. So we have 3 different purities. So we have 3 samples with similar concentration but various purity. We want to understand the influence of purity on the discrimination. And we've studied 2 samples with various concentration but the same purity. To study those samples, we put one of them in the cryo chamber here. And we use a 285 nanometer UV LED to shine on that sample. And the light emitted by the sample on the other side is collected by the PNT. So we have a transmitting geometry with a pulsing LED. And here is a list of the various temperature for which we have done the study. So liquid argon temperature, but also liquid xenon temperature, liquid neon temperature. So various really key temperatures where powering could be interesting. First, let's try to understand a bit better the fluorescence of pyrene. So a ground state pyrene looks like that. If excited, it will lead to a monomer fluorescence, which leads to this series of peaks here around 400 nanometers. Now, an excited pyrene molecule can join a ground state molecule and lead to a dimeric pyrene corresponding to an excimer fluorescence. This will lead to this broader band here around 490 nanometers. What we were interested in is to look at how the pyrene spectrum evolves when the temperature decreases, in particular at liquid argon temperature. So to do that, we replaced the PMT in the previous setup by a spectrometer, and the LED was placed in DC modes so that we have a constant UV intensity. And so for one of the samples, we looked at how the monomer intensity and excimer intensity vary with temperature. So what you see here is that you have the monomer band here, the excimer band here. You see that the monomer band intensity increases when temperature goes down, and a decrease in the excimer intensity when temperature goes down also. So at 87 Kelvin, the amount of 400 nanometer emission is higher than at room temperature. Second thing we're interested in, and that's because our long time constant scintillator is going to need a relatively high light yield. We studied at the light yield of these various pyrene samples relatively to TPB at the same temperature. So here are the results at various temperature for the pore samples. And what you can see is that overall, the light yields are between 35 and 50% of TPP at the same temperature for all samples. Now, let's compare the green curve, the red curve, and the magenta curve. This corresponds to 3 samples with the same concentration pyrene, but different purities. And what you can see is that the purest pyrene in green leads to the higher yields. Now, if we compare the 2 samples, blue and green, with the same purity, but now with different concentration, we see that we have a higher yields with a higher concentration. Last thing we need to look at is the time constants. How long is the scintillation of pyrene? So we've carried out time resolved measurements to try and understand that fluorescence. Here you can see qualitatively 3 profiles of the same pyrene samples at 3 different temperatures. What you see and what we seem to see here qualitatively is that the decay of pyrene seems to get longer when the temperature decreases. Just a reminder that all this profile that we can see here include both excimer and monomer emissions. So we've been able to model this fluorescence through a 3 exponential model, 2 exponential decay, and 1 rise term corresponding to the formation of the excimer molecules. So we carried out this fit for all samples at all the 18 temperatures showed earlier, and we've been able to take out 2 decay times. So what we realized first is that the contribution from the rise term is quite negligible compared to the 2 other decay terms. So here we mainly focus on the 2 decay times. So tau1, which value range between 80 nanosecond at 300 Kelvin and 160 at 4 Kelvin, and tau2, higher values starting from 150 to 350 nanoseconds at 4 Kelvin. And first thing you can see comparing blue and green, 2 samples with the same purity but different pyrene concentrations, is that
1 minute.
The time constants are very similar. But what we can see here is that the pyrene purity reinforces the contribution of the long time steps. So at 87 Kelvin, the decay of P15 is dominated by 250 nanosecond component. As a conclusion, the fluorescence yield increases as the sample is cooled and represent between 35 and 50% of TPB. The decay slows down when the sample is cooled, but still remain much slower than TPB decay, which is closer to the nanosecond order. The fluorescence yield is higher with a high concentration and high purity of pyrene. This sample, 50% pyrene, will be used for the neck coating in deep. We also studied a bit closer monomer and hexamer, which is something I have not shown today, but if there are questions on that. And finally, this sample is dominated by 250 nanosecond component at living argon temperature, which leads to a high potential for alpha discrimination in the neck of the deep detector. The pyrene coating will be applied in the next deep upgrade. And you can see David Galasher talk if you want more details on how the background discrimination is realized. Are there any questions?
Okay, thank you for the talk. Denver had to leave, so I'm helping to chair the last part. Any questions? See people raising hands. Okay, if not, thanks for the nice talk. Let's move to the next speaker, Carolina Garcia.
Hello, good afternoon. Yes.
Can you share screen?
Yeah. Now you are able to see the screen, yes?
Okay, we can see the full screen now. Okay.
This investigation was inspired by my program at the University of Campinas in Brazil. So as you can see, the title is like collection amount studies for the decay measurements. What I'm going to talk about is just like a conceptual approach. So it's like a summary of the concept I would like you to know. As I mentioned, it was inspired during my stay, who starts on May, the first day of May last year, and ends the last day of June. So initially, I'm going to give the motivation of this type of studies. It is related as well with LARSOP, so I'm going just to mention something about it. I bet you already know about how this software works. Then I'm just going to present the detector I used to develop some kind of studies very close to what it is observed in real detectors, and but still a very simple and trivial example of the photon detector system. And this is just to explain what is the light collection amount and which are the implications in the measurements. Then I'm going to end with the conclusion and the acknowledgement. So let's start. I bet you already have been heard about NOVA, which is an experiment in Fermilab, where a neutrino beam is sent to Minnesota, a very far place. We are going to talk about that later. Then also to hear about the TK experiment, which is in Japan. Nova is in US, and in the future is also expected to have a new detector, which is the Deep Underground Neutrino Experiment soon, which the near detector is also at Fermilab. So all these three experiments have something in common besides that they are not located in Europe, and is that they are long line experiment, neutrino experiments, long baseline neutrino experiment, which it means is composed by two detectors, one near detector where an accelerator is used to create the neutrino beam. Then the neutrino travels through the air to a far detector, which has the photon detection system. Of course, you can have also a light collation detector at the near detector, but it's going to be more saturated, or expected to be more saturated at the far detectors. Since this kind of experiment is exactly the same as DUN, and just to keep in mind that in the case of the 2K experiment, the Japan particle accelerator facility is located at the city of 2K, and the neutrino beam travels 2,095 kilometers to Kamioka, where is located the SK detector, also called the Super Kamikaze. And similarly, the NOVA experiment, the near detector is located in Illinois, but the far detector is in the Ash River in Minnesota, which means that the neutrino travels more than 800 kilometers. And something that is under construction, but is expected to be the biggest long baseline neutrino experiment is where the far detector is located 1,300 kilometers away. So this is like the current experiment, but before that, in 2012, there were probably the first of this century experiment, long baseline neutrino experiment, but this one is located in SAR. And the near detector is in SAR, and the far detector is located at the Gran Sasso National Laboratory in Italy. In that case, the distance that the neutrinos travel through the air was more than 700 kilometers. So, yeah, as I already mentioned, we for this type of studies, we were more interested in the far detector because it's less saturated, but in any case, it compromised also a very large volume. So in order to build this type of far detectors, they are built by small pieces that we call it modules. And there is, for instance, there is the protodune, which is the prototype built by the scale with the scale volume of the main detector. And in the case of protodune, is more than 36 meters square. 36 meters square times like a 7 meters as a total volume. what is important for this type of detectors is, you already know that the principle of the time projection chamber. It is that the material you use for the scintillation process. So in this case, Dune and NOAA share the lithium argon material as the scintillation medium where the photons travels from the vertex or where the neutrino interact with the detector. They create new particles. From these new particles is where we study the neutrino properties. And in the case of the photons, when they are produced, they're going to start travel to the far from the vertex, almost to the wall of the detectors where the photon detection system is located. This is more. This is general for all. Most of
you have 4 minutes left.
Okay. So I just put here a paper you can read about it, and in this case, in this particular case, there were 60 modules which just measure the photon, because there are also the other wires, different planes for the ions and electrons collection. Yeah. So when the scintillation material is argon, then we can use they develop a software specific for that, which is called LAR software that you already know. So maybe just I could say that they use Pandora as the pattern recognition to take into account the different physical process that take place in the neutrino vertex. And just for last year, for instance, and this year, or at the beginning of this year, there is this module called RICOV, which makes the reconstruction by using the simulation or by the data, and based on the experimental data, they calculate the number of optical hits in the detector. Yes, and here I just give the complete name because we wanted a detector that is inside the chamber, and we are for this particular model they are not using another specific trigger. So this is like the general data that comes from all the type of events that was saved in this particular file you're analyzing. And just to mention that we are interested only in the photons part, and for that in the simulation, if you just want to run the simulation, you will find out that this package used Gen4 for that. After that, you can run an analyzer module to obtain just a specific root file which has the histogram for the optical hits against the optical channel. What I mean is that this module and this variable is used is in the software. Yes? So what we can do with that variable?
So 1 minute left. Sorry.
Yeah. So before that, I will part detector here, but I'm going to put just the photon detection system at the top, at the bottom. And just to mention here that this one like is a volume, you can take it as a cross section or you can take it as a top view. So I divide the total volume by pieces of 5 centimeters. Sorry, 50 centimeters. So at the end, I'm going to have like a 4,800 detectors. So I'm going to focus in two particular cases for this model. So the photons are going to be distributed along this volume that I already put in the values. And if it is a 5 and above, then they're going to have a hit in the upper detectors. If it is another number below, then it's going to hit the bottom detectors. And if it is in the middle, I'm going to assume that it hits both detectors. So I additionally add that if it is very close to the corners, then the intensity of the light collection of the number of the hits is going to be double, but it doesn't change a lot in the results. So now what we see is, although this is a very preliminary model, what we see is that along the detector, there is no difference between the small volumes, which is what we expect, which we would like to have that like a straight one. Of course, this could happen no matter which random numbers are you using. In other words, I didn't say that. What the idea is that to put randomly or have a Monte Carlo for the initial points of the photon. So I'm going to assume that the detector already have been triggered to the events that I want. Yeah. So I'm going to assume that all of them are going to be detected. And since this is optical hits, it is obtaining from the wavelength and the waveforms of the silicon photomultipliers. So
I'm sorry.
Yeah, sorry.
Maybe you can try to wrap up. Yeah.
1 minute. So although I'm simulating just one case of the photon, in reality, the signal I obtain is the composed of the many multiple waveforms. So in this case, for the simulation, although it's simple, it is very similar to what is in the real experience. So if everything is correct, if our detector is correct, there we are not going to see a difference between the modules, as I already explained, and this happens for many of the runs that you would like to run. So, so what is this light collection amount? So it is something that you calculate after the photon electric field determination. So it's going to change according to the detector you're analyzing, and its value also depends, as we already know, from the type of radiation that you are creating in the detector. And what
So,
it helps.
please try to wrap up. Sorry to interrupt.
Okay.
Yeah. But
no, just to mention that it depends. It is the average of the optical. So you can use it to reduce the uncertainty of the measurements. Yeah, thank you.
Okay.
Thank you to the organizers for this and the university and the financial support for project. You can read the. Thank you.
Yeah, thank you for the talk. Any quick comments, questions? If not, let's thank all the speakers for the session. We'll conclude this session. Don't forget to vote for the poster, and we'll meet in 25 minutes for the next session. Thanks, everyone.